A stellar explosion 1.9 billion light-years away still changed the electrical state of Earth's upper atmosphere.
On October 9, 2022, high-energy detectors across the solar system registered a pulse so intense that several instruments were temporarily saturated. The event received the catalog name GRB 221009A.
Astronomers quickly gave it a less formal name, the Boat, the brightest of all time.
That nickname describes the record of our instruments, not every explosion the universe has ever produced.
Yet statistical studies cited by NASA and ESA suggest that a burst this bright in Earth's sky may be a once-in-many-thousands-of-years event.
The photons had traveled for roughly 1.9 billion years before reaching us. Their source was not nearby, and Earth was not their target. We were simply positioned inside the narrow path of a distant stellar catastrophe, looking down a jet powerful enough to make space telescopes behave as if the sky itself had overloaded them. Long gamma-ray bursts are associated with the collapse of massive stars. When such a star can no longer support its core, the core may collapse into a black hole. Material falling inward can form a hot rotating disk, while magnetic fields and rotation help launch two opposed jets moving close to the speed of light. If one jet points toward Earth, detectors see a gamma-ray burst.
The explosion is not equally bright in every direction. Its apparent violence depends on geometry. A focused beam aimed almost along our line of sight can look vastly brighter than the same event viewed from the side. NASA observations support a collapsing star origin for GRB 221009A, although the accompanying supernova proved unusually difficult to separate from the brilliant afterglow and intervening dust. The black hole was born far away. Its beam crossed intergalactic space without weakening into irrelevance. ESA reports that the strongest gamma rays affected instruments near Earth for about 800 seconds.
That is short compared with a human day, but long enough for the burst to interact measurably with the upper atmosphere.
Gamma rays and X-rays carry enough energy to ionize atoms and molecules, stripping electrons away. Normally, the Sun dominates short-term disturbances in Earth's ionosphere.
During GRB 221009A, instruments usually used to study solar flares detected a response from a stellar explosion in another galaxy.
Researchers found changes that persisted for hours.
The effect was not a mass extinction event, and official sources do not report harm to people on the ground. Earth's atmosphere did what it normally does: it absorbed and redistributed dangerous high-energy radiation.
The unsettling fact is not that the protection failed. It is that a remote event was powerful enough for the protection to register it. The ionosphere begins high above ordinary weather, where solar radiation already keeps gases partly ionized. Radio signals, satellite links, navigation systems, and scientific instruments can all respond to changes there. A burst of gamma rays can add ionization on the planet's night side, where direct sunlight is absent. GRB 221009A therefore turned a layer of Earth's atmosphere into a detector thousands of kilometers wide. The response helped researchers reconstruct the burst after space instruments had saturated. This is an important distinction: the burst did not punch a visible hole in the sky, and it did not make the atmosphere radioactive. It briefly altered the electrical state of an existing atmospheric layer. Measured carefully, that alteration revealed how much energy had arrived.
A phenomenon that began with a collapsing star became a small change in the conductivity of air above our heads. The burst also illuminated material much closer to home. X-rays scattered from sheets of dust in the Milky Way and produced expanding rings in telescope images. The rings were echoes, not physical circles racing outward through the dust. Light that took a slightly longer route around intervening grains arrived later, so the apparent ring grew with time.
ESA reported 20 dust clouds illuminated in this way. Their distances and properties could be studied with unusual precision. A catastrophe in a distant galaxy became a flashbulb for otherwise obscure structures in our own. The geometry is almost domestic. A beam passes through a dusty room and reveals layers that were already there.
Only the room is the Milky Way, the dust clouds are separated across immense distances, and the flash came from the birth of a black hole almost 2 billion light-years away. Calling GRB 221009A the brightest ever detected does not mean scientists measured every part of its peak directly. The burst saturated multiple detectors. Researchers had to reconstruct the missing intensity from instruments that responded differently, from unsaturated portions of the signal, and from comparisons with the known population of gamma-ray bursts.
NASA describes the 10,000-year estimate as a statistical inference.
ESA likewise uses careful language, probably the brightest burst ever measured, with a nearest recorded rival roughly 10 times weaker.
This uncertainty strengthens the story rather than weakening it. Science did not receive a perfect number from a perfect machine.
It received overloaded detectors, atmospheric effects, scattered X-ray rings, and an afterglow seen across many wavelengths. The record emerged by fitting those separate pieces together while marking what remained model-dependent. At 1.9 billion light-years, GRB 221009A was far too distant to threaten life at Earth's surface.
Gamma-ray bursts are sometimes discussed as possible hazards when they occur much closer and their jets align with a planet.
The 2022 event does not show that such a disaster is approaching, nor does it justify predicting one.
It demonstrates something narrower and fully observed. Distance alone did not make the event undetectable. After billions of years of travel, enough high-energy radiation reached our planet to saturate spacecraft and disturb the ionosphere. The inverse square law had spread the energy over an enormous area. Cosmic expansion had altered the photons. Dust lay across the path. Still, the beam arrived with authority. The universe can place an event safely beyond imagination and let its residue touch the air around Earth. GRB 221009A should not be turned into a prediction of an imminent burst near Earth. Astronomers detected it after its radiation arrived. They did not receive an advance warning from the source. Nor does its brightness mean it was uniquely dangerous to us. The event was remarkable because its jet aligned with our view and because modern observatories could measure its effects across gamma rays, X-rays, visible light, radio waves, atmospheric instruments, and dust echoes. No official source used here claims that a similar beam is now aimed at Earth. The scientifically responsible dread lies in the demonstrated scale. A star can collapse in another galaxy, form a black hole, and send a narrow pulse across intergalactic space that still leaves signatures in spacecraft electronics, galactic dust, and the upper air of a small rocky planet. The observation is complete enough without inventing a countdown. The boat gave astronomers an exceptional laboratory for jets, black hole birth, particle acceleration, interstellar dust, and atmospheric response. It also left a quieter lesson. The night sky is not isolated from deep time. It is crossed by signals emitted before complex life had transformed Earth, signals that can arrive during an ordinary afternoon and make modern instruments exceed their designed range. Our atmosphere recorded GRB 221009A for a few hours. Spacecraft preserved fragments of the pulse. Dust in our galaxy drew temporary rings around it. Then the detectors recovered and the upper atmosphere relaxed. The source itself had been gone for roughly 1.9 billion years. What reached us was not the explosion, only its old light. If a dead star can still touch Earth's atmosphere after that journey, what other ancient events are already traveling toward a sky that has not seen them yet?